In planetary science, planetary differentiation is the process of separating out different constituents of a planetary body as a consequence of their physical or chemical behavior, where the body develops into compositionally distinct layers. The denser materials of a planet sink to the center, while less dense materials rise to the surface, generally in a magma ocean. Such a process tends to create a core and mantle. Sometimes a chemically distinct crust forms on top of the mantle. The process of planetary differentiation has occurred on planets, dwarf planets, the asteroid 4 Vesta, and natural satellites such as the Moon. Topic: Heating. When the Sun ignited in the solar nebula, hydrogen, helium and other volatile materials were evaporated in the region around it. The solar wind and radiation pressure forced these low-density materials away from the Sun. Rocks, and the elements comprising them, were stripped of their early atmospheres, but themselves remained, to accumulate into protoplanets. Protoplanets had higher concentrations of radioactive elements early in their history, the quantity of which has reduced over time due to radioactive decay. Heating due to radioactivity, impacts, and gravitational pressure melted parts of protoplanets as they grew toward being planets. In melted zones, it was possible for denser materials to sink towards the center, while lighter materials rose to the surface. The compositions of some meteorites achondrites show that differentiation also took place in some asteroids, e.g. Vesta, that are parental bodies for meteoroids. The short-lived radioactive isotope 26 Al was probably the main source of heat. When protoplanets accrete more material, the energy of impact causes local heating. In addition to this temporary heating, the gravitational force in a sufficiently large body creates pressures and temperatures which are sufficient to melt some of the materials. This allows chemical reactions and density differences to mix and separate materials, and soft materials to spread out over the surface. On Earth, a large piece of molten iron is sufficiently denser than continental crust material to force its way down through the crust to the mantle. In the outer solar system a similar process may take place but with lighter materials. They may be hydrocarbons such as methane, water as liquid or ice, or frozen carbon dioxide. Topic: Chemical differentiation. Although bulk materials differentiate outward or inward according to their density, the elements that are chemically bound in them fractionate according to their chemical affinities, carried along by more abundant materials with which they are associated. For instance, although the rare element uranium is very dense as a pure element, it is chemically more compatible as a trace element in the Earth's light, silicate-rich crust than in the dense metallic core. Physical differentiation. Gravitational separation. High-density materials tend to sink through lighter materials. This tendency is affected by the relative structural strengths, but such strength is reduced at temperatures where both materials are plastic or molten. Iron, the most common element that is likely to form a very dense molten metal phase, tends to congregate towards planetary interiors. With it, many siderophile elements, i.e. materials that readily alloy with iron, also travel downward. However, not all heavy elements make this transition, as some chalcophilic heavy elements bind into low-density silicate and oxide compounds, which differentiate in the opposite direction. The main compositionally differentiated zones in the solid Earth are the very dense iron-rich metallic core, the less dense magnesium silicate-rich mantle and the relatively thin, light crust composed mainly of silicates of aluminium, sodium, calcium and potassium. Even lighter still are the watery liquid hydrosphere and the gaseous, nitrogen-rich atmosphere. Lighter materials tend to rise through material with a higher density. They may take on dome-shaped forms called diapirs when doing so. On Earth, salt domes are salt diapirs in the crust which rise through surrounding rock. Diapirs of molten low-density silicate rocks such as granite are abundant in the Earth's upper crust. The hydrated, low-density serpentinite formed by alteration of mantle material at subduction zones can also rise to the surface as diapirs. Other materials do likewise. A low-temperature, near-surface example is provided by mud volcanoes. Moon's creep. On the Moon, a distinctive basaltic material has been found that is high in incompatible elements, such as potassium, rare earth elements, and phosphorus, and is often referred to by the abbreviation KREEP. It is also high in uranium and thorium. These elements are excluded from the major minerals of the lunar crust which crystallized out from its primeval magma ocean, and the KREEP basalt may have been trapped as a chemical differentiate between the crust and the mantle, with occasional eruptions to the surface. Fractional melting and crystallization. Magma in the Earth is produced by partial melting of a source rock, ultimately in the mantle. The melt extracts a large portion of the incompatible elements from its source that are not stable in the major minerals. When magma rises above a certain depth, the dissolved minerals start to crystallize at particular pressures and temperatures. The resulting solids remove various elements from the melt, and melt is thus depleted of those elements. Study of trace elements in igneous rocks thus gives us information about what source melted by how much to produce a magma, and which minerals have been lost from the melt. Thermal diffusion. When material is unevenly heated, lighter material migrates toward hotter zones and heavier material migrates towards colder areas, which is known as thermophoresis, thermomigration, or the Saurit effect. This process can affect differentiation in magma chambers. Differentiation through collision. Earth's moon probably formed out of material splashed into orbit by the impact of a large body into the early Earth. Differentiation on Earth had probably already separated many lighter materials toward the surface, so that the impact removed a disproportionate amount of silicate material from Earth, and left the majority of the dense metal behind. The Moon's density is substantially less than that of Earth, due to its lack of a large iron core. Density differences on Earth. On Earth, physical and chemical differentiation processes led to a crustal density of approximately 2,700 kg per cubic meter compared to the 3,400 kg per cubic meter density of the compositionally different mantle just below, and the average density of the planet as a whole is 5,515 kg per cubic meter. Theories of core formation. Iron catastrophe. Rainout model. See also: Core mantle differentiation. Notes